The chain rule is the hardest of the rules of differentiation to get used to using because it isn't a rule in the sense that you can't write it down like a formula. It's used when you're differentiating something which is inside something else. So here, 4x plus 1 is inside sine. And what else do we have in life where things are inside something? That's right, pregnant people. And what's inside them? A baby. So, I'm going to explain the chain rule to you using this pregnant lady and a baby. So sine is the mother. Sine is the outside function, the mother, and the baby is 4x plus 1. The baby is currently inside the mother. The 4x plus 1 is inside the sine. And here's the rule, in inverted commas, for differentiating. So what we do is we're trying to differentiate the mother, sine, with the baby inside, 4x plus 1. And what that equals is the derivative of the mother, and you leave the baby inside. Okay, so the derivative of this is sine, of the sine, the mother sine. The derivative, when we differentiate the mother, the derivative of sine is cos, and here's the important bit, you leave the baby inside. So the baby is now going to be inside the derivative of the mother, but the point is the baby is still inside. There's the baby. Oh, cute baby. Now we multiply by the derivative of the baby with respect to x. Now the baby is 4x plus 1, so the derivative is 4. So we multiply this by 4, and that's your derivative. Let's try this one. E to the 2x plus 1. Here's the mother. The mother is the e, and the baby is the x squared plus 1. Okay, so we're going to differentiate the mother. The derivative of e is e. And we must leave that baby inside the derivative now. And then we multiply by the derivative of the baby, which is 2x. So probably nicer to write it the other way around. 2x e to the x squared plus 1. Pretty simple, right? You do get used to it. This is a fun one. What's the mother, what's the baby? The baby is inside, so the baby is 6x squared minus 1, and the mother is to the power of minus a half. So let's differentiate the mother first. To the power of minus a half, well, the power comes down and then changes by going down by 1. That's the mother differentiated. Let's leave that baby inside. And now we multiply by the derivative of the baby, giving us a total of minus 6x, 6x squared minus 1, all to the minus 3 over 2. This one looks a bit complicated, doesn't it? But quite often ones that look complicated, you can just write them a different way, and then they look easy. Like this one, for example, is x minus 3 to the minus 1. It's now pretty obvious that the baby is the x minus 3. That's inside the to the power of minus 1. So the mother is to the power of minus 1, so we can differentiate that. Minus 1 comes down, baby stays inside, changes to minus 2. Then we multiply by the derivative of the baby, which in this case is just 1, giving us minus x minus 3 to the minus 2. Let's look at this example, which sometimes causes people a bit of bother. It's the big question, what's the mother, what's the baby? If we've got sine x squared, the mother is sine, the baby is x squared, so the derivative is cos, that's the derivative of the mother, with the baby still inside, and then multiplied by the derivative of the baby. Probably nicer to write 2x cos x squared. What about sine squared x? What's the mother? What's the baby? It's not obvious anymore, but it should be a lot more obvious if I write it like this, which is indeed what it actually means, sine x squared. Now hopefully you can see now that the baby is the sine x, that's inside, and the mother is the squared. So what we're going to do is differentiate the mother first. The mother is squared. The derivative of squared is 2, whatever it is, and the baby stays inside. And then we multiply by the derivative of the baby, which is cos x. So it's 2 sine x cos x. And when you learn your trig formulae, you'll say, oh, that's sine 2x. Now, obviously, mathematicians across the country aren't saying to themselves, what's the baby? So what the usual way of writing this looks like this. We introduce, not a baby, but the letter T or U or something like that, some other letter, to define the baby, 4x plus 1. So I'm using T, but we can use any other letter really. T is me specifying what the baby is. And then what I'm going to do is I'm going to write down the formula that's written at the top here, but instead of baby, I'm going to write the letter T. So this is what it looks like. dy, let's say the mother is y, by dx equals, the mother is y, dy by dt, the baby is t, times dt, the baby is t, by dx. So this sort of, when you look at it, does make sense in that you think, oh, that dt cancels that dt. dy by dx is dy by dt, dt by dx, and the t cancels the dt, so that's just dy by dx. Yeah, that makes sense. And you can think of it like that, but it's a lot more complicated than things cancelling, because these aren't fractions. Derivatives aren't fractions, they represent the limit of an infinite process, and you can't just go, oh, cancel, cancel. But in terms of thinking about it, you can see these cancel in inverted commas, leaving you with dy by dx, and that is the proper way of writing the chain rule. And this is what it would look like if we did it really properly. We would start by saying y equals sine of 4x plus 1. Then we would define our t, our baby, to be 4x plus 1, and we would rewrite this sentence as y equals sine t. Then we would differentiate y with respect to t to get this part of the equation here, dy by dt. So dy by dx is dy by dt, dt by dx. So we need these two ingredients here. So we would differentiate y, dy by dt, which is cos t. Then we go to the second part of the rule, dt by dx. Here's t in terms of x, and we would differentiate that. dt by dx equals 4. And then we would get these two parts of the equation, dy by dt and dt by dx, multiply them together to get dy by dx. dy by dx equals dy by dt times dt by dx, which is 4 cos t. But t is 4x plus 1, so then we have to put the baby back in, so to speak. So the t is 4x plus 1, so the actual derivative is 4 cos 4x plus 1. And I kind of hope you're thinking that the whole baby thing is a lot easier. I'll show you another example so you can see the connection, because it is important to understand the chain rule in this form. It's just you don't have to think in this way every time you differentiate. So to recap, the chain rule in its proper mathematical form tells us that dy by dx is equivalent to dy by dt, dt by dx, and t is our baby. So if we've got the function that we're trying to differentiate, e to the x squared plus 1, then we can rewrite that as y equals e to the x squared plus 1, then define t to be x squared plus 1. If we then rewrite our function y, we can write it as e to the t, allowing us to differentiate it with respect to t really easily. We then differentiate t with respect to x, giving us 2x, and then pull these together using the chain rule. dy by dx is dy by dt, dt by dx, which is equal to e to the t times 2x, but then we have to remember to replace the t with what it is, which is x squared plus 1, so the overall derivative is e to the x squared plus 1 times 2x. Now, instead of all of that, you could have just done this. d by dx, e to the x squared plus 1 equals, there's my mother, yeah, there's my mother, e, going to differentiate her and leave the baby inside, then I'll multiply by the derivative of the baby. E, leave the baby inside, multiply by the derivative of the baby. Simpler, right? Last thing, a good fun little thing that you can do with the chain rule, which is quite useful. The chain rule says that dy by dx is equivalent to dy by dt, dt by dx. Now what if we take the letter x and replace it with the letter y? What would it look like then? dy by dy equals dy by dt, dt by dy. Okay, so it might not look very exciting to you, but it is quite exciting. So left hand side is 1. 1 equals dy by dt, dt by dy. And you might be saying, well, yeah, obviously, duh, because that cancels that. That's what the chain rule says, so you just get dy by dy, which is 1. But what this is showing us is that dy by dt multiplied by dt by dy, this is a function, equals 1. That means these are the reciprocals of each other. That means if I know dy by dt, then its reciprocal, literally 1 over that function, is dt by dy. Let me write that down here. dy by dt must be 1 over dt by dy, or the way we usually write it is with x's. dy by dx is the reciprocal of dx by dy is something that you might think is obvious, but actually isn't mathematically that obvious. How is this useful? Well, here's a problem that I'm sure you've come across in your day-to-day life and wondered about. X is tan y. What is dy by dx in terms of x? So what are our options here? What are we going to do? We're going to do tan to the minus 1 of x equals y, and then try to differentiate tan to the minus 1, which is not, by the way, tan x to the minus 1. That would be cot x. This is arc tan. Arc tan is the way we write it to make sure that it's shift tan. It's the opposite of tan on your calculator. And I don't even know what the derivative of arctan is, really. No, I don't. So this is just nasty. We don't want to do this. This is not good. We need a better strategy. Well, we can easily differentiate both sides with respect to y, can't we? Derivative of the left-hand side with respect to y equals the derivative of the right-hand side with respect to y, which is sec squared y. Don't worry if you didn't know what the derivative of tan was. You will soon. So dx by dy is sec squared y. Sorry. Not sec squared x, sec squared y. Okay, now the chain rule, this application of the chain rule here says that if we've got dx by dy and we reciprocate it, we get dy by dx. So if we've got dx by dy and we reciprocate it, then we get dy by dx. We just turn them both upside down. 1 over sec squared y. So we're nearly there. We've got dy by dx. We just need it in terms of x. X is tan y. That doesn't say tan y, but when you learn your trig formulae, you'll say, wait a minute though, sec squared is 1 plus tan squared. I learnt that rule. So this is 1 over 1 plus, well, if x is tan y, then x squared is tan squared y. So tan squared y is x. So this is just 1 plus x squared. And now we have dy by dx in terms of x, and we are happy. Feel quite proud of ourselves. So finally, a summary. The chain rule says that the way to differentiate something where you've got something inside something is to recognise what the mother is and recognise the baby. Differentiate the mother, leave the baby inside. The baby is now inside the derivative of the mother, and then multiply by the derivative of the baby. If we wanted to write that properly, we would write dy by dx is equal to dy by dt, don't have to use t, you can use any letter, times dt by dx, which you can sort of think of as saying that these dt's cancel. So in general, for example, you might see a dy and you might change that to dy by dt dt. That's the chain rule in action again, saying that these dt's cancel. They're not really cancelling, but the chain rule allows us to do this sort of thing. The other thing that we can do that's quite useful, same idea, is that we can write dy by dx and say that its reciprocal is dx by dy. So the chain rule sort of tells us that derivatives behave like fractions, with things cancelling, with things reciprocating, with things cancelling. That's what the chain rule allows us to do, which isn't really the case because it's not a fraction, but the chain rule lets us treat it as if it is a fraction, which is quite cool. But in general, I would say use the baby approach for differentiating things like d by dx, like sine 4x. Derivative would be derivative of mother, mother's sine, derivative cos. Leave baby inside derivative. Leave baby inside, very important. Multiply by derivative of baby.